Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Welcome to this course, Marine Energy and Blue Economy. So we have our colleague from University of Michigan, Professor Lee Zhu, and my colleague K.G. Vijay, and I am Professor Abdul Samad. Will be teaching the course. Majority part will be taken by Professor Lee Zhu, and I'll be taking small part, and Professor Vijay will be taking small part. And basic thing in the course is that ocean energy is there. So how to harness? So you need lots of technology. So whenever you develop technology, you need to know mathematics, because you are engineering student. So you need to know different physics and mathematics. So professor will try to give that theories and explanation, all these things. After that, we'll be going for some experimentation also. So Professor K.G. Vijay, he is arranging all this experimentation in our laboratory. We have a web-based facility, so a student can see, and I think he will give some real-life experience thing also through experiment. So it will be very good learning for you. Okay, and all these days, 2 weeks, you should attend all the courses, because assume this is taxpayers' money. Okay, so you are attending, so you are learning. Government is paying for your learning. Okay, so you learn it and utilize professor resources. Professor will be here for 2 weeks, and if you have any other issues, any other discussion, you can do also discussion with us, professor. Okay, and yeah, Professor, you want to speak something?
Okay. Thank you so much, and it's really honor for me get a chance to come here. I know Professor Samet in the past few years, and we write proposal together. We call the paper, and he sent his best student, or one of his best students, to me, Vishnu, right? And when I was student at MIT, I also have classmates and mates from IIT Madras. Okay, currently I have postdoc in addition to PhD student in Vishnu, right, and also postdoc from IIT Delhi. Okay, so I get to here last night, and in the morning we walk around. I enjoy the campus. Okay, it's an honor for me to get a chance to teach you here, and hopefully we can have some more collaboration with IIT Madras, with other university in India, and also I also would like to recruit more students and postdocs from India too. Yeah.
Good morning, everyone. It gives immense pleasure to co-host this GEON program. So I see a lot of people from different backgrounds, right? Starting from neurologic and also mechanical and civil people pitching in. So don't take any tension. We are here to interact. We are here to help you out, and we are here to make it more learning process, right? So in the 2 weeks, you will start with the basic theories, and then slowly getting in what are the technologies that are pitching in, and why the advancements in the conversion is getting delayed, and how we can contribute to the better nation. So that is what the thought process should be, correct? So we'll be working in this process, and towards the second half, wherein Professor Samad and myself will be starting, and then we'll have just to motivate and just to have more interactions, we'll have some experimental activities as well, so that you will have a hands-on experience. So you will be asked to get involved to find out what are things that we do on a laboratory scale, and how this will be transformed to a real world, right? So what are things that we generally do as a research scholar, people who are there, and what are things they generally do, and how you can be part of. Many people have a dream of coming to IITs, correct? So we lay the platform here so that you will get in line to these activities. So for this may be helpful for your projects as well, correct? So you can, if you want to do it later, for example, when you come to final year, so I got motivated. So those things, if you want to discuss with us, we'll be happy to assist you to get in this direction, right? Happy learning. Thank you.
So I have some more thing to speak because regarding administration issues. Whenever recording going on, so that time you don't block your camera. Like if you want to go out also for bio break or something, so don't block the camera. Otherwise, that you have to cut, right? and noise also try to avoid. Okay, and try to attend all the sessions. Okay, so you may have health issue, other issue, that is different story. But if you are in campus, so don't roam around, rather you stay here, you learn it. You came here for learning, right? And government is paying for that. Right? Government is paying for your learning, so you must concentrate on that. Fine. Yeah, if you have any question, then you can stop also, but not to interact when he is speaking. So maybe professor can give some time. So if you have any questions, so they can ask and interact. Okay, so every few minutes or every something like that.
Yeah.
Okay, so when he is speaking, that time if you are interacting, then that will be some distraction for your recording purpose.
So we can have interaction in between or not?
You can make it.
Okay.
You can make it.
Okay.
Okay. Yeah, please come, all come. Yeah. Any other?
Preferably, we would like to take the questions at the end. You please make a note of it so that we can have a more discussion towards the end. So if you interact, if you interrupt in the middle, you will get answers, but may not be getting in a elaborated way, right? So maybe at the end it is better.
Also, after 1 p.m. I'm available too, right? In these days, in the afternoon, and
But
if
you'll
you
be
need-
feeling sleepy, right?
Oh, it's okay.
Because US time, right? So
Yeah. So I'm available to discuss with you. Yeah. Okay.
So professor will be available in NSC too. You can talk to our TS, Appandiraj and Adarsh is there. So both student you can see their backside. Okay.
Yeah.
You can talk to them, professor location, our laboratory location, they can tell. Okay. You can give your WhatsApp number also to them so that they can communicate easily to.
Okay.
Okay. Done? Okay. Thank you very much.
Okay. Thank you.
Yeah, professor, you can
Yeah.
start.
Okay. Thank you very much. Thank you. Yeah. Thank you. Yeah. So, good morning, everyone. I taught this course, Marine Energy and Blue Economy at the University of Michigan. That course was designed for senior students and first year graduate level course. I just understand that we have sophomore in the classroom and we are going to tailor the content, don't worry. And the professor, is our responsibility to design the course according to your level, right? So, and okay, the first half today's lecture is a more introduction. So in this introduction, we have very easy and a lot of pictures you can understand what's going on. Okay, and the second lecture or second half is a vibration scene. Today we are going to have a little bit more equation, so I'm going to adjust that for tomorrow. Okay, so let me see. Okay, and first I want to make an introduction about myself, and through this introduction, I hope that I can inspire you to look into this field. Let me say that way. Okay, I have my bachelor degree in automotive engineering car. Then I have my PhD in I have master in electrical engineering and master in mechanical engineering. I have my PhD in mechanical engineering. Now I'm professor in ocean engineering. So in between, before I come back to university, I worked in a pharmaceutical company for 4 years. You may understand how this link together. Okay, so let me tell you, then briefly you see what we can do, right? And what you can do. Okay, so as I mentioned that car was my undergraduate degree. Tsinghua University is more like a IIT or MIT in China, right? So then I come to US 99, 25 years ago. So then during my master study, I work on the vibration of lithography machine. In between, I also have a dual degree in electrical engineering. And after I finished master, I went to GE, work there briefly on the machine dynamics side, like gas turbine. Then I come back to MIT, finish my PhD degree. I work on the LIGO project, Laser Interferometer Gravitational Wave Observatory. And I work on the vibration isolation. LIGO, this project, 2017, it won Nobel Prize, right? So one important challenge is about vibration isolation. Like you have laser, laser interferometer, or these are isolated from the ground vibration. There are two arms. One arm is 4 kilometer, another one arm 10 kilometer, and we want to detect small change in 10 power minus 21 meter. Okay, so or you walk on the ground, earthquake, or have interaction. So we have to isolate the mirror. Okay, so then after I finished my PhD in 2004, and I went to a pharmaceutical company in Chicago. I worked there as a senior instrumentation engineer. Most of my work is building instrumentation. For example, this left side shows robotic system in the large classroom size to store compound and retrieve compound. And I also built some automation chemical reactor, something like that. So then after that, I went back to university, first in Stony Brook, New York, then Virginia Tech, then Michigan. So, wow, you find, wow, professor, this is odd background. How this happen? Okay, now how this happen. Okay, so as you say, my background, you can say vibration, dynamics, control, mechanical design, or mechatronics design. So how this link together to the current professor in ocean engineering? Okay, so I work in company from 2004 to 2008, and in 2008, US, you say, finance industry crashed down, and oil very, very high in that time. Then in that time, people think how to get energy, right? Because oil price very, very high. I will show you one figure, you can get a sense. So then I think I will work on energy harvesting. In that time, energy harvesting become a hot topic. So look into literature in that time, people get a microwatts, milliwatts energy. If you can get a 0 watts energy like this, you can publish the paper in Nature and Science, right? This figure shows year and number of paper per year. One is conference paper, one is journal paper. In that time, I feel, wow, this will be hot area. I want to jump into this area, right? 2008, I can see this trend. I can get a sense it will be a very hot area, number of paper per year, right? And so, also in that year, Professor Dan Inman, in that time was Virginia Tech, later also moved to Michigan. He gave a keynote talk and about Deng Ha-Tog Award. You say Deng Ha-Tog is considered to be the father of vibration, right? And he gave Deng Ha-Tog Award. His Professor Dan Inman's talk is good vibration. So I'm thinking, wow, how to use the good vibration. So in that year, I met in the conference Dr. J.Q. Sun, and I worked in company for years. I asked Dr. Sun, okay, can you write a reference letter for me? I want to go back to university to become professor. Dr. J.Q. Sun asked me, what are you going to work? I said, well, I want to work on energy harvesting. I have background of vibration, right? I know control. I want to work on energy harvesting. So Professor Sun told me, I don't think you can survive in the field. I said, why? He gave me 2 reasons. One reason is you never work on energy harvesting, right? So how can you convince the funding agency to give you money, right? In United States, you recruit students, you need funding support. And he said, take a look at the Professor Dan Inman's grant, mostly from military, Air Force, NASA, right? You are a foreigner in the country. You don't have background. So this is one reason. Another reason, he said, you say the energy halving. Energy is a very hot topic now. However, energy halving, microwatts, milliwatts, it has a very limited application, right? So cannot address the energy issue. So this inspired me to think, can we, instead of microwatts, nanowatts, this type of energy, can we get larger scale energy? Kilowatts, 100 kilowatts, like that. So this is the way I motivate me to think. Okay, so you look like engineering world. There are a lot of large vibration, like a civil structure, tall building and bridge, right? Like truck and car, railway, like human motion, like ocean. All this is a problem, right? And in civil engineering, automotive engineering, right, and ocean engineering, right, we try all kind of way to reduce the large vibration. Why not take advantage of this? Take this large vibration opportunity, harvest the energy, right? So then look into that. This is very unique opportunity, but also challenging. The reason is small energy harvesting is quite different from the large scale energy. And in that time, the pioneer in this field, like Professor Dan Inman, like other guys, they work on energy harvesting, for example, piezoelectric type of energy harvesting, like a cantilever beam, right? Reduce the more that the vibration, they convert into electricity. And this voice coil and motor, they harvest energy. Traditional vibration is vibration, energy harvesting is a vibration problem, right? You have vibration, you have transducer, then you convert into electricity, no matter electromagnetic coil or piezoelectric, right? So to harvest energy, you just need to meet two conditions. One is match excitation frequency. So if you design your system matches the excitation frequency, you have resonance, the vibration large. Second condition, you match the damping. So match damping have electric damping induced by the harvesting, and mechanical damping the same. You get a maximum power output. This is more like impedance matching. Okay. So for larger scale energy, for example, the tall building, the car, and the ocean, right? What's the difference? Let us say what's the difference, this figure, okay. So larger scale energy harvesting is more complicated. So you not only vibration, let me say, first not just a vibration system, right? So you need to understand the source. For example, the wave and buoy interaction, right? How the wave propagate in the ocean, right? So then you also need to understand the vibration dynamic system. After that, you design your powertrain system to convert into electricity. Then you need power electronics and control to make things work. Overall, it's a much more complicated system. So for larger scale energy harvesting, you need a system level thinking, right? System level approach, not only vibration. So it is multidisciplinary. It needs a vibration, design, control, electronics, smart material, right? So the first priority for this type of system is to control the vibration, not to reduce the vibration. I happen to have all this type of background, right? From vibration, control, electronics, and for the system hands-on experience. I can build hardware, I can do vibration analysis, right? I can also have electronics background. So this is why I jump into this field, large scale vibration. Okay, so not yet. In that time, large scale vibration, I mostly focus on like a first project, like only car, this type of thing, right? And this is, I want to show you two projects I work on, okay. So first is vibration from car suspension. You drive the road, the car will vibrate. I have my background undergraduate degree automotive engineering. This is my first project. Okay, I work on the vibration from the car suspension. It's interesting, and this is highlighted in Virginia Tech News for several days. The title is "Good Vibration." So it happened to be exactly as the keynote talk given by Professor Dan Inman that inspired me to think about large scale energy. So this figure shows you have 2 to 4 millimeter vibration, you can get 100 watts energy. Compared with milliwatts, microwatts, this is already not much larger. Okay, so and the second project, which is my first U.S. government support project, is tall building vibration, energy halving, and vibration control. Right, this shows Taipei 11. There are a big ball, and it's 700 tons mass on the top of the building. So it can get 100 kilowatts type of energy, the peak energy in the level. Okay, so I write a proposal to the National Science Foundation on this project. Okay, so the tall building vibration and the stroke can be 1 meter. And where the frequency for this one is 7 seconds. Okay, so such kind of energy level and vibration amplitude and frequency is very close to the ocean. So therefore, and this I work on here, and then gradually more to shift my focus to the ocean, because let me tell you why. Okay, quickly, and the ocean side. One side, this amplitude and stroke will be similar to the civil structure, right? On the other side, and in that time, I design hardware to convert the vibration system energy into electricity. Later, in ocean engineering, we call the power takeoff. So, and in the past years, I designed different type of energy converter, and I test in the ocean and lake, okay, and also offshore wind side too. So let us say ocean energy or marine energy source, and or blue energy. You say this map, 72% of the Earth's surface are covered with water, right? There are huge different resources from marine, right? And including ocean wave, tidal current, ocean current, right, river current, as well as ocean salmon, offshore wind, even marine biomass, right? So take ocean wave example, and in United States, according to the NRE's National Renewable Energy Report, okay, it can, in United States, the total ocean wave resource can power all the grid 1.27 times. If you consider technical feasibility, and ocean wave can provide 1/3 electricity for the country. So, and ocean wave source is large, and power density is large too. And power density, ocean wave power density measured is different from solar or wind, right? Is not measured by square meter, and scientifically it's measured by kilowatts per wave front length. So you take this map and as okay, like Indian side right here, you look at this, you get a sense. You can get 5 to 10 kilowatts per meter, right? And in U.S. West Coast, you get 30 to 40 kilowatts per meter, and the East Coast like 20 kilowatts per meter. And if you convert X into electricity, according to Professor Fanny's literature, okay, they said that you can get 2 to 3 kilowatts per square meter. How much is it? 2 to 3 kilowatts in solar, right? It is a sunny day. The solar density is 1.5 kilowatts per square meter. You consider the electricity, convert electricity 10%, 20%, you get a couple of 100 watts per square meter, right? So wave energy density is much larger than the solar. Okay, it's also much larger than the wind. So as you know, this decade is called ocean science for sustainable development, and it's claimed by United Nations. Okay, the decade of ocean science. So, and blue economy. This slide shows European Union's vision about blue economy. Basically, blue economy is sustainable use of ocean resource, right? And with considering sustainability in the future. It includes a lot of traditional things in the ocean. For example, fish farm, offshore oil, right? And also include a lot of new industry sector. For example, offshore wind, ocean biomass, ocean energy, like that. So, and this is the United Government's vision about ocean energy, specifically Department of Energy in 2009. They come up power blue economy vision, and power blue economy. So basically, there are two major application side. One's power at sea, including you harvest energy, you use that energy to power underwater robot power fish farm, right? Another is resilience and coastal community. So you have energy to produce fresh water, to release disaster, right? To power remote community. So people ask, wow, Trump has become new president, right? So second term, he didn't like renewable energy. So what we can do? Take a look at this two White House document. Okay, the second one is Decade of Vision for Ocean Science. Okay, that is published in Trump when Trump was president. Okay, another is Biden when Biden is president. He linked that in ocean energy into ocean climate change. Okay, so I believe more energy in the next 4 years will continue to grow, right? So given that when Trump's first term, he emphasized energy, renewable energy too, okay, from ocean. So ocean energy, and the first patent was 200 years ago, 1799, right? However, it's still infant around the world. So after 100 years, ocean wave energy, and in 1940s, Japanese researchers used it to power lighthouse, right? So if you link the ocean energy with the oil price, this shows oil price, right? And take a look at this here. 1970s, the first oil energy crisis, and 2000, this second. Now is the third, right? And you plug another figure here, okay? So this number of papers, right, and the oil price, you get a sense. First, energy crisis start the more energy research, right? And then 2008, I mentioned in that time the oil price is high, right? So then I mark this one. I move back to university. I will tell you that's not the reason I put this arrow here, okay? So anyway, nowadays each year the published paper is more than 2,000 per year on the ocean energy side. Why 2008 is important? Okay, aside I come back from industry to university. Actually, the main reason is 2008 is the first year U.S. Department of Energy support more energy research. So, and in the past years, okay, 2016, they create the Water Power Technology Office, and with the budget $45 million per year. Now, in this year, specifically actually last year, this year federal budget didn't come out yet. So the budget is about 140 million. They increase very, very quick. So, and the federal government spends the money about 1/3, 38% in the first quite a few years till 2002. Okay, 38% to industry, 36% to national lab, and a quarter to the university side. Even after that much investment, ocean wave energy, if we say what's that ocean wave energy, right? And you don't know what's that, right? I say wind energy, you say, oh, big tower, 3 blades, right? Wave energy, there's no convergence. You don't know which one's the best, right? You even don't have uniform criterion to judge which one's the best. So take a look at what's going on in the literature, right? And even how to classify the energy, wave energy converter, there are different ways. Some based on the location, some based on structure, some based on power takeoff energy conversion mechanism, right? You can have onshore, near shore, and offshore, right? Okay, you can have buoy to move up and down, right? You can have flap, right? You can have this type of device, overtopping, whatever like that, and many different, okay. And some literature, some published paper, they said, okay, and they found more than 1,000 different type of energy converter. And okay, so there's no research convergence. Why is that? Okay, take a look at here. Okay, this is one type of wave energy converter. You have buoy, move up and down, and drive a generator with the power transmission, then drive the power electronics side. Okay, so you get a sense how complicated it is. You have wave energy to excite mechanical motion, right? Power capture device, then convert into mechanical motion. After that, mechanical motion convert in electric energy, right? Electric energy is very irregular. Then you need power electronics eventually deliver to the end user, right? You need a control system to coordinate everything. More important, beyond the engineering, there are different other challenges like economic side, like environmental science, like social science, policy, community, right? You can say wave energy is really multidisciplinary research. This gives you sense, right? The ocean wave energy is really multidisciplinary research. So you need ocean engineering, right? Ocean structure design, power takeoff, power electronics, dynamic sound control, material manufacturing. And this shows engineering challenging. Outside engineering, we need to also know environmental science, social science, and the policy, government, community, right, and economic side. So we need a multidisciplinary research. Okay, this is why I jump in. This is why I told you why I jump into this field, right? I got trained in the dynamics and control, right? And I also have engineering design experience and double-E degree on the power electronics side, and I also learn a lot of fluid. So recently, I get a lot of social community engagement. So this figure so my field is pretty large. Okay, this figure shows what's going on in the research in our group. So I jumped into this field 2 years after I work in the university, right? First, like car suspension. Second, the tall building. 2010, I transfer the power takeoff I designed to marine ocean engineering side. Then we design different type of wave energy converter and 500 watts, 10 kilowatts, 100 kilowatts, right? And I also use that energy for different application. 2019 Department of Energy come up power blue economy, right? The concept actually, and 2015 I already got a National Science Foundation money to do the power blue economy work. In that time, they power the buoy for the ocean monitoring, right? So then more recently, we use that energy to power fish farm, power island. So more recently, I shifted my focus, extend my research to the marine current and offshore wind energy. So Here, I would like to give you a little bit sample project, give you sense what kind of course we are going to learn during the 2 weeks. So basically, through this example, you get a sense what kind of thing we are going to learn. When I open this course, my motivation is to train students with the capability to do research in the field. Okay, so as I mentioned, 2010, I pay attention to the morality side. In that year, I read a paper written by Professor Facau in Portugal. Professor Facau built the first European Union grid connected wave energy converter. Like in Portugal, Pico Island is 400 kilowatts wave energy converter. It's operated for 19 years, from 1999 to 2018. The device looks like that, okay, alternating water column. So look like a bucket, put upside down, the wheel move up and down, and get air push in and out. Draw the generator to rotate one direction, right? So this alternating water column. So, and this is our first try of a human being for about farm scale wave energy converter is in Scotland. So they built this device. You can sense how large that. This farm is 2 megawatts. So it's working in that way that can give a sense. Okay, this hinge motion here to draw a piston pump. Piston pump draw accumulator, hydraulic motor, right? And through this check valve to convert this bidirectional motion into one direction fluid motion, then drive the generator. So as you can see, both design, they try to make a system from 2 direction to 1 direction. So this design is so complicated, hydraulic systems, it failed in several months. Okay. So in that time, I work on there. In that time, I already developed shock absorber and for the car and also for the turbine. So I shifted the application to the ocean energy side. This gives you sense. Okay, you say the wave energy converter just move up and down, right? This test in the ocean. Okay, and here this buoy move up and down, drive this motor. Take a look at this one. Okay, especially pay attention to this motion of generator. Okay. You see the both screw drive this up and down, drive the shaft to rotate 2 directions. Here the generator rotates 1 direction. So the key part is this gearbox. This gearbox, you can say the bidirectional motion rotates drive the generator 1 direction. So in between, we put a 2 one-way clutch. And this one-way clutch similar as our bicycle gear, right? Or the engine starter. So, and this bicycle gear, you say 1 direction directly engaged, drive the shaft. Another direction, this one-way clutch disengaged, this get engaged. So the motion transmitted from here, bevel gear, drive the generator in the same direction rotation. I give them name mechanical motion rectifier. And because there's another concept in the electric domain and the electric voltage rectifier, right? Electric voltage rectifier, this figure shows the center tapped and transformer. This diode, right? Then this Mosen capacitor to convert. Now we convert by the AC voltage into DC, right? And using two important elements is semiconductor diode and Mosen capacitor. In mechanical domain, we have one-way clutch and we have flywheel. Okay, so what's the advantage? right? Advantage, sure, you generate a rotor one direction always. In that way, we can generate a DC voltage. However, that's the main advantage, not main advantage. The main advantage is high efficiency. The generator will always rotate one direction, constant speed. In that way, this efficiency will be higher, and also reliability is higher, right? And as you say, from fatigue theory, you have Goodman curve, average mean stress and average stress, right? You convert such kind of force stress into one direction, and the certain reliability will be higher. Okay, and another thing is higher compact. Right, I mentioned that hydronic system, check valve, so complicated system. Now our system is just a small gearbox, right? And another advantage is high bandwidth. If you have such kind of larger rotation inertia, larger mass, you know the system is hard to control. Now our rotation inertia acts as a flying wheel, and that will help us to make system control easier. Okay, so it will have higher bandwidth. Okay, so we build a system and we test in the ocean. That is 5 miles offshore, right? It's a small buoy we tested 10 years ago, 2014. And later we build a 10 kilowatts device. They test in National Renewable Energy Lab area, and as you can see, we also build a 5 kilowatts power electronics, a 50 kilowatts power electronics system. So overall, this system will give us efficiency 81% for the 500 watts per prototype, and we test regular, irregular, compared with the hydronic system, like 15%. Okay, we already also built a hydronic power takeoff, and it takes us 2 years to double the efficiency from 15% to 30%. Now, this system we can easily build to have 80% efficiency, right? Irregular way we test, we get 40 to 60% efficiency. So, and that is the first Department of Energy funded project in our group, and we form a multi-disciplinary team, including gear dynamics expert Professor Robert Parker, and also power electronics Professor Kai Lo. Okay, then we include national lab area, and we also include industry partner Resolute Marine, THK, and later we add University of Maine to do the test. This is SME, Mechanical Engineering magazine's highlight of our work. So we talk about power takeoff. However, to put system in the ocean, we have to consider everything. For example, the power source, right? The fluid and structure interaction, the electronic system, and grid connection. So here, this gives you sense about how the dynamics and hydrodynamics plays a role. And you put the buoy in the system, right? You can model the system. In this class, you are going to learn how to do this type of modeling. And in this modeling, we need to understand the so-called added mass, radiation damping, hydrostatic stiffness, and excitation force. So actually, it's just 2-degree freedom vibration system. Okay, added mass means the surrounding water move together the buoy. There's energy, and radiation damping means when the buoy move up and down, it generates wave. The energy propagate out. So that's the radiation damping. Okay, so on dynamic side, at this 2-body system you have a tank, and this single body system you can fix. What's the difference? Okay, and this is the result we did. Okay, and this shows the 2 different mass. We optimize the parameter of power takeoff stiffness, power takeoff damping. Also, we optimize the mass ratio. This mass compared with this mass. Okay, and this one is single body case, right? There's no other mass, just reference. Okay, and this figure shows the result. Okay, as you can see, this figure, if you have two body system, and the energy can double, power can double. Okay, so it can achieve higher power than single body case. What's the reason? You can take a look at the damped natural frequency. If you learn vibration, you understand the square root k divided by m, that is the natural frequency of single mass case, right? You have double mass case, you have two vibration frequencies. Here, the reason you have double the power output is you match the excitation frequency with the damped natural frequency. At such kind of natural frequency, then the two bodies move out of phase. When the buoy move up, the other tank move down. Out of phase motion give more power to the system. So this is the reason. Okay. Overall, give you sense, hydrodynamics vibration is important for this wave energy converter, right? So, and overall the efficiency is two parts. One is the capture width ratio, another PTO efficiency. We already gave the sense about PTO efficiency. The capture width ratio is related with the hydrodynamics. So this figure shows the result. Okay, if you have single body, right, and or you have flat, or you have tank shape, right, and you have the different wave excitation. This is power flux. Okay, and you can see if you use these two buoy case compared with this reference model, right, and this fixed second body, and the capture width ratio can be almost doubled. Okay. Anyway, you get a sense that the energy conversion is multiple steps. The hydrodynamics computation is important. Overall efficiency is the hydrodynamics efficiency and the PTO efficiency. We get 20%. So this figure also you can say, get a sense, wow, the wave is really irregular, right? The peak power is very large, average is small. This is called peak to average power ratio, right? And this peak to average power ratio really hurts us. The reason is you have to design the system. For example, you have 100 kilowatts rated power output. The system output you need 1.5 megawatts, because 1.5 megawatts will be the peak power. When you design the mechanical system, electric system, you have to consider the maximum force, maximum voltage, maximum current, right? So the system is over-designed. Just imagine that way you drive a car, you mount a jet engine in your car, you wouldn't have good efficiency, right? You need some way to address this problem. This part we are going to learn also. So for this one, we also design the power electronics and control. Here, the generator, you have internal inductor and capacitor or internal impedance. Then you design power takeoff, right, to translate the motion into generator motion. However, now the voltage is very irregular, right? We design the PWM control the power electronics, and so the control is more like impedance matching, right? You design the feedback control so that you can control the impedance, and with this we design the power electronics testing in lab. This shows if you put a resistor load, and you get in this small scale system, we get about 10 watts, right? And if you use power electronics, we can double the power output. Okay, the reason is this impedance. Okay, this is still suboptimal control. Why? Why we call it suboptimal? Okay, you ride a bike, if the road is flat, you have no problem. You can ride there, right? And up here is no problem. Down here, what happens? You need brake. Without a brake, your bicycle run out of control, right? The reason is you use one-way clutch, right? So here is similar thing. You use one-way clutch because one-way clutch is in this power takeoff system. Your system can run out of control. Your pedal cannot control the bike to move back. Similarly, and your wave energy converter, the generator cannot control, give energy back to the buoy. Sometimes you need to cancel the stiffness, right? Reactive control. This system, you cannot implement that. So in electric domain, what people have done, okay. So I don't know how many guys you have electric background. Okay, and in electric domain, there are two most important elements. One is diode, another transistor, right? And transistor, we already say the diode in the mechanical domain is more like a one-way clutch. And actually, transistor, there are two functions. One is amplifier function, another switching function, right? In DC-DC converter or in power electronics, what people have done, for example, here, they replace this semiconductor diode with transistor. Transistor, you can control this. It's more like a switch. They control on and off. In that way, the energy stored here can go back to the original system, right? This is active electric rectifier, right? And now we can create such kind of domain, such kind of system in mechanic domain. What's here? Okay, so this is core design concept. What I want to tell you, we design, consider a very unique PTO, but we find it's run out of control. And then we design an active motion rectifier. Well, how we achieve that? Actually, I mentioned that I have my bachelor degree in car, right? And car, inside the car, there's another very important element, electromagnetic clutch. And in India, it's very hot in summertime. You want to have air condition, right? Air condition, you push a button, then the air compressor work. You get air condition. You push the button, actually, you go through electromagnetic clutch. It engage the electromagnetic clutch. And in that way, the engine drive the compressor. Here, this system, there's two electromagnetic clutch. So in one direction, we directly engage. Then the generator drive same direction. Meanwhile, the generator can act as motor, drive the buoy system, right? And or this engage, another engage, the power transmitted from here to here. It's different from just now passive one-way clutch. This power transmission is two direction. What means the buoy can drive the generator can drive the buoy. Then with the system can be in control. Okay, so in this project, this is active motion rectifier. Okay, this is the project we got together with Stevens when I was in Virginia Tech, and also with company Resolute Marine. So that is floating wave energy converter, and you have flap to drive the system. Okay, I mentioned this is innovation, active motion rectifier, and you can see another innovation. What's this video first? You can say this buoy, right? Not buoy, this flap, like here, it rotates very, very small angle. Let me stop here. And where this system and the motion is very, very large, right? So that is dual flap, and we put this dual flap almost out of phase, and then that way the more than certain the force almost zero, the certain Q balance, then we have large motion. So a third innovation in this project, again, PTO, okay. So I show you this figure about people, one company, I don't name whom, okay. They want to design the direct drive PTO. This PTO generator is 5 meters, right? It's a huge device. So, and this test in area, they have difficulty to move inside the lab. They have to make modification of the structure to move inside. The reason is the direct drive, the rotation speed here is so small. For example, if you put a generator on the hinge drive you can calculate. So if you have 30-degree, 10 seconds rotation, the RPM average is 2 RPM, very, very small, right? And where generator, you need a higher speed. So how to achieve higher speed? This is our solution. Okay, you can see this one, this flap rotate one, and they have belt mechanism, right? And this belt like pony. So you can convert this motion, very slow motion compared with 100 RPM to drive the generator very high speed, right? So that is another transmission innovation. In that way, we don't need a 100 gear ratio. You 100 times gear ratio, the torque is huge and the friction is large. Now we easily address this problem. So this problem we go through the multi-scale design. Okay, sure. Okay, and then basically we design the 4th gear system first. They conduct a hydrodynamic study. Then we did a 1 to 10 gear tank test. Then we design 1 to 2 gear system, and including hardware and loop control. Then we come back to update our design to the 4th gear system. Okay, so I stop here. After lunch, we can continue the lecture and also including the vibration system. Hopefully you get a sense, right? Wave energy converter, in summary, is really, really multidisciplinary research. You need to learn vibration. So this is why second part is vibration. You need to learn the wave dynamics, how the wave potential flow, this wave theory, right? And then you need to learn how to do the modeling side, and you need to learn how to design the PTO, how to do the control. And wave energy system, you cannot do everything in the simulation, right? You have to do some hardware. This is why Dr. Vijay will give you some hands-on tank test, give you sense about hands-on stuff. More energy also including ocean current and offshore wind. We can give brief introduction about offshore wind energy in the course. Okay, so I stop here. Let us come.